Hi everybody. So in this video, we're going to look at damped harmonic motion. And the presence of damping leads to a differential equation of a form where we have an acceleration, a velocity, and a displacement term equal to zero. And there's three types of damping. There's an overdamped motion, a critically damped motion, and an underdamped motion. And we'll talk about how a differential equation can give rise to either of these types of damping. So if we look at overdamped motion, this is where the auxiliary equation has two different real solutions. The system undergoes heavy damping, which means it moves smoothly towards equilibrium without any oscillation. And you can see this in the red graph where we've got displacement against time. There's no oscillation, and it does move quite smoothly towards the equilibrium. So a real life example of this could be the suspension system on a luxury car, where when it goes over a bump, it slowly returns back to normal without bouncing up and down. And you can see in this example, the auxiliary equation would be m squared plus m minus 2. So the distinct real roots would be m plus 2 and m minus 1. So the roots would be -2 and +1. Okay? In a critically damped motion, where the auxiliary equation has a single repeated real solution, the system is in a state of critical damping. This allows it to return to equilibrium as swiftly as possible without oscillating. You can see in the green sketch that this curve goes to equilibrium much quicker than the overdamped motion. Okay? A real life example of this would be the shock absorbers on a mountain bike, where you have to return to equilibrium very quickly as there'll be multiple bumps. And you can see that this differential equation would lead to m squared plus 10m plus 25. This will lead to one real solution where we have m plus 5 squared. So m would be equal to -5. And then the final type of damping is underdamped motion. This is where the auxiliary equation has complex solutions, and the system experiences light damping, meaning it oscillates while gradually decreasing in amplitude towards equilibrium. And you can see from a blue sketch that whilst it's oscillating, the peak of the oscillations are reducing until it does go back to equilibrium. An example of this could be a swing at a park, where it goes back and forth until gradually stopping. And you can see that the auxiliary equation would be m squared plus m plus 2 will equal 0, which would lead to a pair of complex solutions. Okay? So these are the different types of damping, and it's important to understand how to identify the different types through the discriminant of the auxiliary equation. And we'll focus on this as we progress through the video. So we're going to work through two questions. In the first question, I'll go through, and in the second example, you can try. So we're told that a particle Q moves along a straight line at time t, and its displacement from a fixed point on the line is x, and this describes the motion of a particle. We're given these initial conditions. We need to find x as a function of t, and then to find the displacement when t equals pi over 4, and finally to determine the type of damping. So the auxiliary equation would be m squared plus 6m plus 9 will equal 0. So this will have one repeated root when m equals -3. So the complementary function will be of a form a plus bt multiplied by e to the -3t. If you're not sure how to get this complementary function, you should check out my previous videos on methods of differential equations. So now we need to find the values of a and b, and we can do this using the initial conditions given here. We're told that the particle is at rest when t equals 0. So what do you think this will give us? If a particle is at rest, then dx by dt will equal 0. This means it will have no velocity at that point. So we can use the fact that when t equals 0, x equals 4, and when t equals 0, dx by dt is also 0. So if we begin with t equals 0 and x equals 4, then 4 will equal a. This term will become 0, and this term will become 1. So 4 will equal a. And then we need to work out dx by dt and set this equal to 0. I'll just rewrite the equation with that known value of a. And I think the easiest way to differentiate this is to use a product rule. So we'll let this equal the u term and this one equal the v term. So dx by dt will be u times dv to negative 3e to the negative 3t plus v times du. The constant will go, the t will go, so we're just left with b. Then if we substitute in our values, dx by dt is 0. We know t is 0, so this will just become 4. E to the negative 3t will become 1, so we'll get negative 3. This term will become 1, so plus b. So therefore, b must equal 12. So the displacement as a function of time, we'll substitute in our known values. So we'll have 4 plus 12t multiplied by e to the negative 3t. So that's part A. For part B, we need to use this particular solution to work out the displacement when t equals pi over 4. So x will equal 4 plus 12 times pi over 4 multiplied by e to a negative 3t, so negative 3 pi over 4. And when we work this out, we get x to be approximately 1.27 meters. And then for part C, state whether the motion is heavily, critically, or lightly damped. Well, we need to find the discriminant of this auxiliary equation. So we'll have b squared, this will be 6 squared, and we'll have 4ac, so 4 times 9 will give us 36. So you can see that they're equal. 36 will equal 36. This means we'll have a critically damped system. So if I quickly sketch this, we'll have a displacement against time. Then we'll have a smooth curve which quickly goes to equilibrium without oscillating. And when t equals 0, we'll have 1 here, 0 here, so we'll have a displacement of 4. Okay? Let's try example 2. So do you want to read through this question yourself and try and work out x as a function of t, and then to work out the displacement when t equals pi over 6, and then determine whether it's heavily, critically, or lightly damped. You can pause the video, and when you come back, we'll go through the solution. Okay, so I'll come back if you want to go. So we'll start with the auxiliary equation. We'll have m squared plus 2m plus 10 will equal 0. When we solve this, we get that m is negative 1 plus or minus 3i. So because we have complex solutions, the complementary function will be e to the negative t, this negative coming from this real part, multiplied by a cos of 3t plus b sine of 3t. And then we need to work out the values of a and b using our initial conditions. And again, because we're told that when t equals 0, the particle is at rest, this means that dx by dt, the velocity, is also 0. So if we start with x equals 3, e to the 0 is just 1. The cos of 0 is 1, so this term will just become a. And the sine of 0 is 0, and this will eliminate the b term. So we'll write that x is equal to e to the negative t multiplied by 3 cos of 3t plus b sine of 3t. And then we'll use our second condition here to work out b, which means we need to differentiate this. Again, I'm going to use a product rule. We'll let this equal our u term, and this will be the v term. So dx by dt will be e times dv. This will give us negative 9 sine of 3t plus 3b cos of 3t. And then we'll have the derivative of our u term. This will be a minus e to the negative t, and then the v term. So I'm not going to expand this out anymore. I'm just going to substitute in when t equals 0 and dx by dt is 0. So 0 will equal, this term will become 1, this term will become 0. So we're left with the cos of 0, which is 1. So this will just give us 3b. And then this will become negative 1. The cos term is 1, the sine term is 0. So we'll just have negative 1 times 3. So therefore, 3b will equal 3, b will equal 1. So the displacement as a function of time will be 3 cos of 3t plus sine of 3t. And then for part B, determine the displacement of a particle when t equals pi over 6. We'll substitute pi over 6 into each of these. So x will be e to the negative pi over 6 times 3 cos, and when you multiply pi over 6 by 3, we get pi over 2, plus the sine of pi over 2. The cos of pi over 2 is 0, so this term will go, and the sine of pi over 2 is 1. So we'll get the displacement as e to the negative pi over 6, which is approximately 0.592. And then for part C, state whether the motion is heavily, critically, or lightly damped. Well, the discriminant, we've got our b term, so b squared. We've got 4 times the 10, so you can see that the b squared is less than the 40, so therefore the system will be underdamped. I'll quickly sketch what this will look like. So we know the displacement will oscillate with the peaks decreasing until it becomes to equilibrium. Okay? Well, thank you very much for watching. I hope you found that useful. If you want more practice on this, you can download the worksheet and view the online lesson from my website, mrmathematics.com. I'll leave a link below.